Welcome back again to the IEEE standard arithmetics, and next talk is by Tom. Yes, thank you.
Thank you for the introduction. I will talk about LaTestGen, which stands for Interval Arithmetic Test Generator, which is developed in cooperation with Jedich, Martin Lehmeyer, and Professor von Gutenberg, whom many of you may know. And LaTestGen is a unit test generator that can interpret a domain-specific language and translate it into some source code that will test an implementation of interval arithmetic standard, or even just interval arithmetic. So here's the outline of my talk. We will first talk about the motivation behind that. Then I will introduce the domain-specific language we have defined so far, and give some examples for you. And then we will talk a little bit about the design, and I will give a short summary about it. So first, motivation. If we look at possible implementation of the upcoming IEEE standard, we see that there's an environment the implementation works in. So there's the CPU, there's the compiler. The compiler may have some combination of switches turned on, and then there are libraries we have seen in macro slides that he uses NTFR to implement that. And all these things constitute the environment, and it's a big black box. And we really don't know if there might be an error or not. So we have two sources of possible errors in this implementation. The first is the implementation itself. There could be an error in our algorithm when we do some computation. And the second error can be introduced by the environment. And the first is not so easy, but it's manageable. We can do a proof that the algorithm is correct. But still, there could be influences by the environment, and we can't check the environment completely. So, but what we can do is we do some sample tests. This is the standard thing to do in software engineering. We do some sample tests on a subset of values and try to gain confidence in our implementation by that. Okay, but how do we specify these tests? Ideally, we would specify all these tests using some abstract representation, and we propose a domain-specific language for that, and that is common, and that can everybody use. And then you have to provide a means to run these tests on all possible environments and implementations. So what would be the benefits of that? Benefits would be that the tests must only be written once. So not every implementer of the standard has to consider what tests to run and what cases there will be. There was a discussion on the mailing list a few weeks ago, and there was mentioned that this will be a huge test set, about 5,000 to 10,000 test cases. So you can see there's a lot of work to be done there. The second thing is we can do it in a well-readable format. So the implementer can easily gain access to the material and see what kind of tests will be run there and where his implementation may have a fault or something. Then the developer of the library can also use this as a regression test while developing, and that will speed up the implementation process. And then it also gives us confidence in the implementations, and especially the user. So a user can just download an implementation, run hopefully the tests on his environment against it, and has at least some confidence that the implementation will work. Okay, let's talk about the domain-specific language. So this is the main thing here. First, the generation process. So we have some test specifications, and they are written in the domain-specific language. Then there's our generator. The generator will just pass the domain-specific language and translate it with a given strategy into unit tests for the platform. And we have to that's it. Okay. The important requirements for this domain-specific language are, of course, an interval data type. We need that. Then there are number types and the Boolean type. We need that for result types and for the lower and upper bounds and stuff. We also have to consider that the number literals have to be given in hexadecimal binary format, because sometimes we just have to, we can't rely on the conversion of the decimal floating point number we have entered, because there could be errors introduced there. Then we need type variables, because we could compute in single or double precision or something. And since there are so many test cases, we also need a way to comment on them, to distinguish them. And just reading some numbers won't help us with that. So comments are important. And of course, we need to define operations that have multiple arguments and also could have multiple return values. Okay, here is an example for the declaration of variables. And you can see a variable is introduced just with a dollar sign. This is common in many languages. And a value is assigned to the variable with the equal sign. And then there's the specification of the type, followed by the actual data. And this is here in hexadecimal format, just for as an example. And then we have here a lower and upper, an upper lower and upper limit in different formats. And we can see here how an interval is defined. An interval also carries a precision, and then it has a lower and an upper limit. And we see here we can reuse variables. Of course, it wouldn't make sense any other way. So, and then there are special values for infinity, and there's also a special value not seen here for the empty set. Okay, this is a simple test case that tests the addition of two numbers. We have first the name of the function, so everybody knows directly what is called here. And then we have two intervals specified that will be given as arguments to the function. And we then say we assign a value, and that is the test. This computation should yield the same value as stated here. So this will be translated into a unit test case. And here we have an interval as result and the comparison. And here we see another test that yields not an interval but just a number in this case. So this is possible too. Okay, this is a little bit more complex example, and this is mainly given because you can see here there are comments. And important is the comments are carried over into the generated source code. So when I have the source code generated for my specific implementation, I can also directly read there what will be tested and don't have to switch back to the domain-specific language. And then there are tags. There are few tags right now that can help build up documentation about tests. Okay, so now I will give an example for the code generation. This is just a prototype, so the code generation is done for interval, for Boost interval library. Yeah, this is just a bisection, and bisection is not in the standard right now, but anyway, we have a variable defined with the expected output. And then we call the function, and we see here that the function has two result values, and they are just separated by commas, so they will both be tested. And this is what will be generated. First, the lower and upper bounds are specified, declared and assigned. Then the intervals are generated, and okay, there's the expected interval for the second parameter, and we have the bisect here. The bisection is performed. This has been automatically generated, and the first and second values are called and saved. And then here is the test case generated with Boost testing, and we have the requirements here. And this will be automatically checked against the generated code. So now a little bit about the design, because this is important for people who want to introduce a new language or a new implementation or a new testing framework. These are the things that can be changed or that can be extended. First, we can extend to other programming languages. Currently, we support Python, Java, and C++. And the testing framework can also be switched. So we have Google Test and Boost Test and stuff. And then the interval arithmetic library must be changeable. And all that has to be done is to provide templates that can be translated into code by the generator. So this is the class design. We have these three interfaces, and these are the interfaces that have to be worked on. If I'm just writing a new implementation in C++, for example, I will just deal with this interface and implement the template. This has to be done in Java, and you can see here there is the implementation for CPP Boost arithmetic library, and this is the one that generated the example in our case. If I want to port to a new language, I have to do all this work too, but it's not that hard. It's mainly tokens have to be specified, and the comment tokens have to be specified, such things, and the general skeleton for the unit test has to be here. Okay, yeah, this is just more detail on that. So if I have to introduce a new language, I need the comment token, standard imports and definitions, like include statements and stuff. I have to provide the basic structure of the test file, just a function or even a whole class in another case. And then I can also give custom methods that will always be generated alongside the generated code. Then if I want to add a new unit testing library, I need the imports and definitions for this library, then the basic structure of the test suite and the test case, and of course the assert function we will use to assert that a given test has succeeded or not. And then there is the important part I talked about last, the arithmetic library specification. Here we need a mapping, maybe, a mapping from the functions that will be called like add and sub and mid or something to the function calls in the library. And this is the main work to be done, but it's really easy, it's straightforward. Okay, a short summary. We can use with LaTestGen a domain-specific language to specify a complete test set for the interval arithmetic standard. And this LaTestGen can be easily extended to support other implementations and other environments. And then implementers get an easy way to check their implementations. They can use it as a regression test set. And also users can check an implementation in their existing environment and can gain confidence that everything will work out as expected. So this concludes the talk, the last talk for today. And thank you for listening. And now I'm open for questions.
Thank you. So, questions? Expert in implementation.
What happens if a function is missing? Is it easy to add it to your framework? I mean, if someone has a bit and the other one has a radius or whatever.
If a function is missing, you have to add it first to the framework, yes. So we aim to provide all the functions in the DSL that will be specified in the standard. But if there are more custom functions, you would have to add them first to the test generator and then the mapping.
What we found? Is it difficult?
No. We use a parser generator, Java CC, to generate the parser for the DSL, and you would have to specify another rule to include your function. That is not too difficult. Yeah. And then as soon as the parser generator knows your function, you can just implement the mapping and it will be done. So there are two steps there. Another question?